Morning, everybody. My
Good
name is
morning.
Susan Greeman, and I am the Principal Asset Management Advisor for Greeman Asset Management Solutions, which is a firm headquartered in Winnipeg, Manitoba. I also want to say good morning to all the members and friends of the Manitoba branch of the Institute of Asset Management, and to let you know as well that our branch was formed this summer, so it's quite new. And since forming, we have participated in 2 national events, one dealing with water utilities and another dealing with power utilities. But this one entitled The Anatomy of Lifecycle Value Delivery is our first Made in Manitoba professional development seminar, and no doubt the first of many to come. We're thrilled by the numbers. At last count, I think last week, Wednesday, we had about 123 persons that had signed up. I haven't gotten the final numbers yet, but I hear that it is north of 150. So thank you very much for a tremendous response. We are thrilled to have these talented professionals donate their time as panelists. So today with us are Paul Crocker and Dr. Lucas Marino. As the speakers are presenting, I will invite you to put any questions that you may have for them in the Q&A box. So there's a question box there. You put it in there and I will be able to retrieve it from there. And you can put it in there as you go along and I will be able to pull it out during the Q&A session. So I will begin by introducing Paul. So Paul is a 20-year employee of Kansas City, Kansas Board of Public Utilities, where he is in his 14th year as the supervisor of maintenance at the Nerman Drinking Water Treatment Plant. A full copy of his bio is included in the event site, but I will tell you that he is proudest of the fact that last week he turned a grandpa to a beautiful new granddaughter. So congratulations to you and your family, Paul.
Thank you.
Paul, you're welcome. Paul will be presenting a series of mini case studies on how an asset management approach to maintenance and reliability improved lifecycle value delivery at the Kansas BPU. Paul, I'm just going to put you into presenter mode and ask that you share your screen and go ahead.
All right. Have I got the right screen up there, Suzanne?
Yes, you do.
All right. Well, thank you for that great introduction, and I'll get started because I've got probably more content than I should for a 30-minute presentation. So, as Suzanne said, I'm a maintenance supervisor, 14 years of experience in this job at the water treatment plant, but close to 30 years in the power and water utility here in Kansas City, Kansas total. Slide. BPU is a publicly owned administrative agency at Kansas City, Kansas. It's self-governed by an elected 6-member board of directors. BPU is the largest combined power and water municipal utility in the state of Kansas. We have over 100 years been providing clean drinking water and electric power to the residents and businesses in Kansas City, Kansas. We have a 120 square mile service area, 51,000 water connections, and 63,000 electric service connections that serve the residents and businesses in Kansas City, Kansas. Our mission as a utility is to focus on the needs of our customers, improve the quality of life in our community through safe, reliable, and sustainable utilities. So in this picture is what I have purview over day to day, and that's the maintenance in the drinking water treatment plant. We get our source water from about 100 foot below the Missouri River through an alluvial aquifer. So really the first source of our filtered water is the Missouri Riverbed. As you can see in that source water picture, the water coming into our plant is fairly clear, usually less than 1 NTU in turbidity. And you can see the other jars there, the processes of water through to the finished product on the right. So enough about the plant. I just wanted to give some context. This presentation is about our journey at Nerman Drinking Water Treatment Plant, and it's about bringing value in the O&M phase, which is the longest phase in the asset's life cycle and hence the biggest contributor to life cycle value delivery. For us at BPU, it's about operations, maintenance, management, and laboratory staff working together to solve problems and deliver value, multifunctional and multidisciplinary. Values achieved in and by the treatment processes we've improved by removal of defects and waste, and through the improved operating and maintenance processes and procedures that happen at all stages of the physical assets' lives in our care at the treatment plant. Today, I'll be presenting 5 case studies about how we've improved life cycle value delivery at BPU Nirman Water. Case study 1 is air compressor system redesign. Case study 2 is aqua ammonia defect elimination and risk management. I've got 3 or 4 slides there. Case study 3 is a combined clear well defect elimination, multiple things there. Case study 4 is asset condition management with lubrication. And case study 5 is chlorine storage reduced risk to operators. It's case study 1. We had 2 compressors installed in 2000 when the plant went online, and they were retired in 2018. They were 50 horse water-cooled rotary screw compressors. And there's a lot of processes that rely on compressed air at the plant, mainly filter and pump valve actuation. The problems with these compressors were becoming excessive in 2016 and 2017. We were experiencing an increase in random failures, increases in iron and particle counts in oil samples. Vibration analysis indicated mechanical looseness in the wetted rotary screws. Cost of a new rotary screw would have been nearly half the cost of the compressor, and longer than a few days lead for most major repair parts. We also had very poor service with the local brand reps, and we couldn't really tolerate the risk of being without an additional compressed air compressor. 2, the water used to cool the compressors was significant. Anecdotally at the time, it seemed like a huge waste, but no calculation was done at the time to see how much. Let's take a look at that now after the fact, since hindsight's 2020 and all. So as I said, the plant was designed to have 2 water-cooled 50 horsepower rotary screw air compressors for redundancy. The operation mode for 18 years was 2 compressors, 1 in service and 1 in standby. However, both ran with water through them regardless of the running state, 24/7, 365 for cooling. The manufacturer of these compressors estimated 7 gallons a minute, plus or minus, needed for cooling of the compressors. Water used calculations for the 2 compressors. So it's 2 compressors, 8,760 operating hours in a year, 420 gallons per hour. That's 7,358,000 gallons of water a year. So water in the utilities is billed usually in CCF, that's centum cubic feet or 100 cubic feet, and that comes out to 74,806 gallons of water for 1 CCF. So monthly, 615,450 gallons of water were used for cooling, which could have been sold for our customers for $2,667. Annually, that's 7,385,400 gallons of water we were using for cooling could have been sold for $32,000 if purchased by our customers. Here's the kicker. For 18 years, these 2 were in service. They used 132,937,200 gallons of water for cooling, which could otherwise have been sold to our customers for around $576,000. That's a pretty significant operating cost. Energy use for the compressors was around 6,482 annually, since only one was in service at a time and the other was on standby. The babies were reliable for 18 years. They used a lot of resources, but they used a lot of resources of treated water that could have been otherwise conserved, chemicals and energy, or in water we could have otherwise sold to our customers. Again, 132 million gallons of water at $576,000 over their life of operation just to cool the compressors, not including maintenance costs. I guess the point of that statement is that design choices matter more and cost more in the long run than they do in the construction phase. 2018, we commissioned a compressed air study, and it determined that the 50 horsepower compressors were actually too large for the plant. They recommended 40 horsepower models that were also water cooled, but we really didn't like that option. We decided to change out the compressors, and we chose to go with air cooled because they wouldn't waste water. We also decided to purchase and install only 1 per year to spread the costs out and to give our operators and maintenance staff a chance to learn, operate, and maintain the new equipment. There were no water calculations for these, obviously, because there were no water going through them, and they're still in the same operating mode, 1 in service and 1 in standby. These newer compressors consume around $5,200 in electricity annually, and that's about $1,226 less than their predecessors, and they also require fewer PMs per year. So that's case study 1 out of the way. Case study 2, high failure rate for PVC heads. Pictured at the center of the slide are an operator with full face respirator and PPE. A metering pump below that and surrounding images are all 4 sides of a single ammonia metering pump head made out of PVC that had multiple stress cracks from exposure to aqua ammonia. 29% aqua ammonia at that. This was the problem to be solved. In our system, we have 2 mechanical diaphragm pumps, 2 heads on each pump for feeding of aqua ammonia into our finished water to produce monochloramine for EPA's disinfection requirements. The failure rates for these heads was several times a year, and a HAZOP RPM study recommended that the PVC components exposed to aqua ammonia should be changed to stainless steel. At each failure, the heads aqua ammonia would leak out, and an ammonia sensor alarm would notify the operator a leak was occurring. The control system would close the supply valve to the metering pumps, and an operator had to immediately don a full face respirator and PPE and assess the problem, figure out how to rectify the problem and get the ammonia feeding again in less than 30 minutes. So for maintenance costs, Maximo started collecting maintenance data in 2007, missing corrective maintenance and PM maintenance for anything before that. However, from 2007 through 2010, we used 8 of these PVC heads between both ammonia metering pumps for a combined total repair cost of $10,624 in parts and labor for that specific failure mode. To solve that defect, our internal machine shop used a new PVC head to make 4 copies in all stainless steel. Roughly 16 hours to fabricate each head with scrap stainless, so cost was internal labor only. And since their manufacturing installation in 2010, we've had 0 failures for this component. We've also replaced the heads. Once we replaced the heads, we also replaced all PVC distribution pipe in the plant for aqua ammonia with stainless steel, eliminating that source of defect. Case study 2.9. The plant was designed for use with 29% aqua ammonia. And from 2008, roughly, we used the 29% concentration. In 2008, a risk management plan compliance audit brought some things to our attention. 29% aqua ammonia is above the EPA's 20% threshold for toxic substances and posed unnecessary risk to the environment, plant, and personnel. 29% put us in EPA's high risk category where we didn't want to be, and the 40 CFR requirements were requirement for each operator to be trained and competent in operating procedures for the covered process, a requirement for refresher training at least every 3 years, and anytime updated or new procedures prior to startup of a process after a major change. Requirement to train employees involved in mechanical integrity of the process to ensure they can perform their jobs and tasks in a safe manner. And they should also be trained in hazards of each process and how to avoid or correct unsafe conditions. The main one here being a review of those items every 3 years and a multi-day audit with internal and external auditing. Aqua ammonia was 29% aqua ammonia was unnecessarily dangerous to work around. It was especially dangerous if it escaped into the atmosphere, and we didn't want the risk. It wasn't worth it. As we saw in the previous slides, it was also fairly damaging to PVC components, pipes, and heads, even though it wasn't supposed to be that. So we went to 19% aqua ammonia as a much lower and safer concentration than the 29% concentration we had previously. And it's a relief not to have to worry as much about it. As asset management's a multifunctional approach, this change effort took internal engineering and operations to come up with a good solution. Operations and engineering found that 19% aqua ammonia could be used with only metering pump stroke and speed adjustments, which were well within each pump's capacity and capability. We still treat the aqua ammonia system as though it's under the risk management plan and with respect, and it saves us around $7,000 a year in chemical costs, which is a nice bonus for the change. This is the last of the ammonia-related slides, but it was worth mentioning because it cut out a bunch of PM work. And unfortunately for the slide, I couldn't locate a previous state photo to use, so we'll have to use the photos I've got in image. Components listed as 1, 2, and 3 are used to ensure dry air is delivered to a 20-pound air blanket on top of the liquid ammonia in our 2 bulk storage tanks to prevent it from boiling. I've got some labels, some items numbered that were causing a lot of PM work orders to be generated. Item number 1 is a housing for ceramic desiccant beads for taking excess moisture out of the air, blanketing our aqua ammonia bulk tanks. 2 is a visual moisture indicator. The color changes from green to yellow to let us know when to dehydrate the desiccant beads contained in number 1. And an operator doing rounds daily would look at the visual indicators, and if they were yellow, they would switch to the second desiccant dryer, not shown, but was previously installed where item number 3 is in the photo. They would then issue a work order to dehydrate the saturated desiccant beads. This is affixed to those PM work orders. Number 3, a desiccant membrane dryer was selected to replace a second desiccant dryer, not pictured. It is sized for the system and has completely eliminated the PMs to dehydrate saturated desiccant beads. The work order numbers prior to the dryer, we had 51 total monthly work orders. Total labor hour for those was 88 hours. Total labor cost, $3,361. The last work order for the desiccant rejuvenation was on 10/21 and 19. Since then, that saved roughly 34 hours of labor in the last 2 years alone. Cost of the membrane filter was $1,500. ROI has already been achieved. This unit has ran flawlessly since install, keeping the air for the ammonia blanket dry at a chilly minus 15 degrees Fahrenheit pressure dew point. Item 1 was left in service in place as a backup in case number 3 was out for service. So we have redundancy covered there. Case study 3, combined clear well problems. These 2 photos are of water quality analyzers for turbidity and NTU, chlorine residual in milligrams per liter, pH, and temperature in Celsius for finished water for a couple of turbine regenerative pumps with a failed impeller pictured below. This is a very important area of our plant for operators. It's where we gather data from finished water quality to report to the state KDHE for EPA compliance and to the Partnership for Safe Water. The Partnership for Safe Water is an unprecedented alliance of 6 prominent drinking water organizations. The PSW's mission is to improve the quality of water delivered to customers by optimizing water system operations. The PSW offers self-assessment and optimization programs so that operators, managers, and administrators have the tools to improve performance above and beyond even proposed regulatory levels. Problems experienced in this area that we needed to address. Number 1, air in the sample stream caused pump impeller damage and turbidity problems. The turbidimeter would see the air in the sample, and that would cause false high turbidity readings. High turbidity readings cause the EPA KDHE turbidity requirements of less than 0.35 NTU and Partnership for Safe Water goals of finished water turbidity of less than 0.10 NTU to be higher. And the turbine regenerative pumps don't like to pump air. No pump designed for water really does. Parts and maintenance, time to rebuild the oversized pumps was excessive. Air was causing damage to the pump impeller over time. You see as the photo above, it would damage the keyway and actually drive it into the stainless steel impeller. A complete new pump was $1,500 and spares were expensive. Rebuilt pump and parts cost around $500 or $900 to rebuild that pump, not including its installation, and keeping spares to rebuild those pumps was expensive. So it causes other problems. Aeration of sample water to online turbidity analyzers. Sample point was too high on a pipe, but we didn't need to move it. And the turbine regenerative pump was serious overkill for the application. It was capable of pumping around 300 feet ahead at 4 gallons per minute. So 2 solutions were employed to correct these defects. 1, a smaller 1/8 horsepower magnetically coupled pump capable of 26 feet ahead at 18 gallons a minute for $434 new was installed. It's considered a run to failure and with a spare always on the shelf. This pump doesn't like air either, but it's far more resilient than its turbine regenerative predecessor. The source of aeration was confirmed using a technology that hadn't been previously considered versus speculation. and the technology is FASTIC for detecting friction, impacting, and turbulence. And I'll talk about that in the coming slides, where I'll show how we came up with a solution to the error and eliminated the problems. For years, it was assumed the error in the sample line was due to oxygen concentration in the cold water, but we were unable to see through the pipes, so we just didn't know for sure. We'd really grown quite tired of the problems and wanted to get to the cause of it. We had recently acquired an SDT 340 and an SDT Ultra Checker for various condition monitoring uses around the plant. The 340 had been sent off for its annual calibration, but we still had the Ultra Checker and decided to take some structure-borne readings around the pipe. Well, ultrasound is a fantastic tool for finding friction, impacting, and turbulence. And in this case, it was the air bubbles combining and breaking apart that was easy to hear and caused increased decibel readings. Put the magnetic probe on the pipe and record its reading in decibels and mark it on the pipe with a dry erase marker. Those points in the photo on the left represent the dB readings the Ultra Checker observed. Readings were highest midpoint up both pipes, but dissipated downstream from the 36 to 48 inch intersection of the pipe. We had proof in concept finally that it was air. Now only one thing remained: confirmation and solution, as we'll see in the next couple slides. So the pumps had already been moved away from the sample point in previous work, so we isolated the analyzers, disconnected the sample lines from the corp stop and valve, and connected a 1-inch clear PVC tubing and let it drain to the floor. It was immediately apparent that air was the cause of the problem. So in this video, I don't know if we'll reshow, you can see the air that was actually going through the tube when we were looking at. Image 2 is of the complete finished solution, a large clear PVC weir. The third image is a close-up of the sample point and lets you see the simplicity of the design: a straight nipple T, clear Schedule 80 PVC pipe going up to release air, clear PVC tube feeding the pump of water free of air. The fourth image is the result of replacing the turbine regenerative pumps with magnetically coupled pumps of a much more appropriate size. So this is the current state with some areas I've circled here. Number one is that we're applied to the sample system. Air is no longer a problem. 2 is the turbine regenerative pumps replaced with smaller, cheaper, and more reliable magnetically coupled pumps. 3 are analyzers that were replaced with much more modern design, eliminating moving parts, lower cost parts, and are more reliable versus the older technology. And fourth, and most importantly, is the partnership for safe water goals are met. Too far ahead, sorry. Upon review of this year's partnership statistical reporting data, the plant was able to achieve an annual average finished water turbidity of 0.03 NTU. Comparing this information with the prior year's data, the annual average finished water turbidity is the same as 2019 and 2020. Where we were able to meet our prior year's goal of individual filter effluent in-service turbidities at or below 0.10 NTU for the 99th percentile for each month. Our operators have worked hard to maintain our current goal of 0.1 NTU or lower before a filter is placed in service. In addition, all our turbidimeters were installed with individual filters, combined clear well, and plant effluent. After evaluating several turbidimeters, BPU decided to go with new Hawk TU5300 and TU5200 benchtop turbidimeters. These were installed in 2020, and at this point, they have performed extremely well. The new turbidimeters are much easier to clean and calibrate, and we hope to see some savings on maintenance and calibrations. We have recently started replacing some of our online chlorine monitor as well. We hope to include those in next year's report. And most significantly are the happy operators and plant management who no longer have to deal with problems in this area of the plant. Case study 4, CMMS and SCADA driving oil analysis. For the longest time, Oil in our large medium voltage motors was changed on calendar year from installation regardless of operating condition or oil condition, which is what the motor O&M says to do. The oil was changed, and that needed to be changed. We wanted to move to quarterly analysis based on run hours so that every 2190 hours of operation, we use Control System Historian to feed a homegrown program we call WW interfaces that can take a control system data point and made it to a Maximo asset meter. Maximo then uses the meter reading to elapse at PM, and when the PM hits the 2190 hour mark, work order is generated to pull oil samples and bottles to take samples from upper and lower bearings. Those are sent off to the lab, and then we didn't do maintenance based on the results of those, and these are the most common actions. If high in particle counts, we filter the oil, filter carts, and resample. If high in iron, we generate an ad hoc vibration ultrasound work order to see if there's a change from previous quarterly readings. If viscosity has changed significantly, we'll either sweeten or change. Doing work this way gives us a good idea what's going on with our motors and helps us better maintain them for a longer life versus the old ways. And the final case study, chlorine storage reduced risk to operators. The plant was built with an in-building but isolated chlorine storage room. It's protected from accidental release of chlorine by a gas scrubber system. It has 3 chlorine sensors that when activated turn on the scrubber to ventilate the room. The problem with this design initially was that the leak detectors would cause an alarm when there was an electronic component within the sensor or the sensor board that had failed, and when there was a small leak, which thankfully hasn't happened often. The alarm would notify the control system a leak had occurred, and an alarm would pop up on the SCADA, which was a good thing, but it didn't let them know which leak detector was in alarm. And it didn't let them know the concentration of chlorine the leak detector was seeing. The practice then was for the operator to don a full face respirator, enter the chlorine storage room, identify which of the 3 leak detectors was in alarm, and if possible, find the source of the leak so it could be immediately addressed. No one really liked that arrangement because it was inherently unsafe, especially on the evenings and weekends when no one else was here. So we made a change to remove that risk to personnel, and I'll talk about that on the next and final slide in the presentation. This was the solution of the problem. We extended each chlorine leak detector's display to an isolated hallway just outside of the chlorine storage room and in one large panel. We extended each specific weak point to the SCADA system with a 4 to 20 output through the display so that operators can see that level of chlorine in parts per million that the detector is in alarm showing. Operators no longer need to enter the room, and that's a huge improvement in safety. And everyone is very happy with this solution. So I think I got talking a little bit fast, so I'm kind of at the end of my spot there, Susie.
You know what? That was awesome, Paul. Thank you so much. Very, very insightful. We'll dig a little bit deeper into it in the Q&A session. So our second round of, and let me just get Luke set up. Our second round of presentation case studies will be by Dr. Lucas Marina. Dr. Lucas Marina is the founder and owner of the East Partnership. He spent 21 years as both a machinery technician and a naval engineering officer in the United States Coast Guard. He then founded Marina Consulting Services and worked in several senior logistics engineering program manager roles for military acquisitions, including Army Landing Craft and the Navy's Columbia Submarine Program. And again, a full copy of Dr. Marina's bio is included in the event site as well. So he will be presenting a case study on the application of 3 supportability analyses, namely reliability-centered maintenance, level of repair analysis, and maintenance task analysis. Luke, over to you.
Awesome. Thank you, Suzanne. And Paul, that was awesome, man. I really enjoyed the pictures. You did a much better job of bringing some visual stimulus to your presentation than I did. But yeah, I really enjoyed that. That was really good. Thank you so much for letting me sit in your presentation.
I think
Okay, yeah, no problem. Yeah, so this presentation is going to be a little different than what you're probably used to, because you're probably not used to hearing a life cycle engineer talk to you about how to approach different perspectives on analysis, while coupling that with a presentation on an actual case study. And so hopefully you enjoy that perspective. It is a bit unique, and I've had great luck with sharing these things with different engineering communities over the past 2 years. So something I would like for you to consider is that the people that manage and engineer and support your assets, they're really good at what they do, right? We hire specialists to do these jobs. However, sometimes we get stuck in these silos of work, and we sometimes lose sight of exactly what it is we're analyzing. Are we producing a product, or are we producing a function for a user? Are we producing some value for someone else, or are we looking to perfect the thing that we are doing, right? So as an analyst, what I usually try to tell the analysts on our team is to remember that you're focusing on two different things. You're focusing on analyzing a actual designed physical asset, but you're analyzing its future activities as well. And that's really where supportability analysis kind of makes its impact. Outside of influencing design decisions, maybe in Paul's example, different types of materials for the pump or different piping configurations, we would have input into those design elements. But most importantly, what we're thinking about is how we're going to support these elements once they're out in the field and in the user's hands. And so we want to analyze both the physical asset and the activities that will be required to support that asset in the field. And we refer to that as sustainment. Okay, so we're going to sustain our assets. Okay, so why should anyone care about any of this, right? We've had our hands on these complex assets for years. Why should we look at any of this any differently than we always have? This work is demanding. You have high levels of complexity. You are managing large quantities of data, and you're trying to make very good decisions with that data. And the more you wrap your mind around the perspective of the analysis and the work you're doing, the better your decision making will become. And this lends itself and leans on the standardized processes and tools that you have. But as managers, we get a little leery investing in some of those things because they're normally very expensive and they take a lot of time to implement. So there is some hesitation to adopt new methods because of that. And so what you end up with is a situation where people kind of try to avoid doing some of the complex analysis that can really pay dividends for them down the road, right? Because it looks like it's complex and it's difficult. There's not a lot of guidance on how to do the analysis. There's a lack of understanding of whether it really has an impact on their organization or not, or what the potential impact could be, because the moment the analysis is done, you don't reap the benefit of the decision. You have to make the decision, you have to invest the time and energy into implementing the solution, and then you get to reap the benefits. And then, of course, there's the wonderful topic of software, right? There's many people that lean a little too heavily on software being the solution, and it creates this false sense of security, right? Software is great for organizing and processing data, but it's not going to do your analysis for you. And even if it does, you still have to make the decision, right? So you have to take it all with a grain of salt. So if we look solely at life cycle analysis of things, it doesn't look very attractive to us. But if we look at the activities that are impacted by the ownership and operation of our assets, well, then we start to see value because we pay for activities, right? We're used to stroking a check for a physical asset. We bought the asset, we installed it, and now we have to pay to operate it and to maintain it. And those are activities. So let's look at the case study a bit. So the asset that I performed my research on is a military afloat asset. It could be any ship, it could be any plane, it could be any train, it could be any manufacturing plant equipment, it could be anything with sufficient criticality and importance and a significant investment for your organization. And when I mean criticality, I mean it's critical to the operations of your organization. If you're in production and manufacturing, this would have a very negative impact on your operations if the piece of equipment were to fail. So we have, in this case, a significant complexity because it's a system of systems of systems in ships. We have operational availability of the asset is critical. It's the prime thing that the owners are worried about, is making sure that this thing is out there doing its job. The critical system failures will absolutely negatively impact its availability, right? If these systems go down, the engines go down and you can't make power, or you can't produce electricity, this would be a bad thing. And then, of course, paying for corrective maintenance, trying to fix things that break gets very expensive very fast, particularly when some of these systems are very much controlled by original equipment manufacturers, and you don't necessarily have the ability to change the design or configuration with your own staff in a way that wouldn't negatively impact you. And then, of course, preventive maintenance is something that we all plan to implement on complex systems. And in these cases, they require a lot of resources to complete the preventive maintenance actions. So these, ships are a great candidate. So let's look into it a little bit. Okay, so supportability analysis. And this is an element of lifecycle management and asset management. If you own a complex asset of significant value, and if you are managing the life cycle of that asset, you should be interested in how components in that asset are going to impact its operation, right? And its ability to deliver value to your organization. So there are things like failure mode effect and criticality analysis that occur as part of a reliability-centered maintenance program that look at how specific components of equipment are going to fail. And if they fail, how will they fail? And when they fail, how will we know? And what will our response be? Okay, so the FMECA helps us do that with critical items. And it also helps us understand the impact of those failures on the operation of that equipment and other equipment in its system. So it's important that the RCM happens in a way that identifies the critical functions of the equipment and potential failures. Now, once we've done that, we kind of have a good idea about what maintenance needs to be done to prevent those failures or correct those failures once they occur, because that's part of the FMECA. And now that we have that information, we can start looking at something called maintenance task analysis. And that is our ability to capture all of the detail associated with those maintenance solutions. So in the FMECA, we identified potential failures, and we created what's called the why. Why are we doing maintenance? Because the FMECA identified potential failures that could be either mitigated, eliminated, or benefiting from some maintenance action. Now that you've told me I have to do something, some activity, we should analyze that activity to figure out what its impact is going to be on our resources. Maintenance task analysis does that. So now we're much smarter about the asset. And now that we have this knowledge and data about the activity, we can go make some decisions. And so we conduct what's called a level of repair analysis, or a LORA. And the LORA will help us understand whether we should repair it, should we throw it away, should we replace it, and if we do the repair, who should do the repair? Should we do this ourselves? Should we hire a contractor to do this? Should we send it to the OEM? Do we even have options at all? Okay, the LORA will help us with that. And in totality, when you take all of these analyses and put them together, you realize you're supporting the asset. Really, that's what this is. That's why they call it supportability analysis. How easy is it going to be, or how difficult is it going to be for us to invest in the resources to execute the maintenance activities and maximize the operational availability of the equipment? So a lot there, right? But it's really simple. Okay, now what's included in supportability analysis? Let's look at the two primary things, the maintenance task analysis and the LORA. And like I said, the LORA, or the maintenance task analysis, is going to give us a lot of the who, what, when, and where, okay, about the maintenance activity. We're going to talk about what skilled labor is needed. We're going to discover what tools and resources and supplies and special equipment, technical manuals, technical documentation, what contracts are going to be required to support us. And in the heart of it is a step-by-step procedure to complete the activity, right? So for all those maintenance planners out there, or people that fund maintenance planners, it'd be really important if you knew how much that activity was going to cost your organization as an activity, and what each step was going to be, how long that step was going to take, and what resources were going to be needed in each step of that activity. And then what you have now is a total view of the impact of that one maintenance activity on your organization. So instead of looking at a pump, you're looking at a maintenance activity around a pump. And it starts to make a little bit more sense for people that fund and support maintenance, because we don't buy things, right? We're funding activities that support the things. And that's really where the value of the maintenance task analysis starts to come alive for people that fund and support maintenance. Now, the level of repair analysis is very analytical. It's great. It does require a dedicated effort. You can use it early in the life cycle to influence concept and design, and then you can use it during construction to help make engineering decisions for future support. Because now in construction, you actually have a physical asset to put your hands on and use. And then as the asset rolls into use with a user out into the field, you can then do the level of repair analysis to ensure that the sustainment and maintenance plans that you have in place to support that asset are realistic and feasible, right? And that you're making good decisions based off of data and logic and not just guesswork, right? So you have data that you've collected about items that are needed to support the activity. You can associate costs with those items, and then you can start looking at comparative cost analysis. And so we're going to break this up into a few different phases. Okay, so when we look at a maintenance concept, right, we say, how are we actually going to take care of this equipment? We've done the FAMICA, we've done the MTA, we've done the LoRa. Now we're looking at all the world of work that then radiates from those analyses and supports the activity. Are we going to need certain parts for consumption? What about just raw supplies? Oh, sorry. What about training? Does our staff have sufficient training? Are they of the right technical skill level to do this work? What about contractors or original equipment manufacturers? Do we need them on site? Do we need contracts in place that we don't currently have? Do we need to reinforce existing contracts, modify them, establish new contracts, maybe get rid of some old ones? And then of course there's tools, special tools, hand tools, all the tools. And what's missing here is special equipment like stands, test equipment, those types of things. And then of course, where in the maintenance organization will this activity occur? So are we going to do this locally on site? Are we going to remove the equipment from the site and take it to a different location on our premises with a different team, a more advanced technical team to do the work? Or are we going to take this equipment off-site and send it to a off-site tech or to the original equipment manufacturer? And when you look at the totality of this, you say, okay, my maintenance concept for this is that we will take care of 80% of the work. We've drawn the line in the sand here. We're going to invest in the skills, tools, training, and resources up to this point to do all of these activities. And then that's our investment in this maintenance concept. The remainder of the work will be done off-site with an original equipment manufacturer, and we've got the support infrastructure in place for that. And that is the top. That is the icing. That's the rest of the story. And then, of course, we would iteratively review this, and I recommend every 5 years, or unless something significant changes with your plant's configuration, and move about smartly. Go execute the plan. And if it needs adjusting, adjust it. But make a good decision and then go do it, right? Because the action is where the money is. Okay, so let's look at the simple flow of a level of repair analysis. And the first phase of a LoRa is this non-economic analysis where we gather all the information about the asset, we learn about the activities, we do the maintenance task analysis. We say, give me all that stuff, give me the procedure, give me the list of parts, give me the list of tools, give me all this stuff. Now let me just think about it. Let me look at this and say, is this feasible for us? And an example for this case study, we had brand new ships and we replaced diesel powered ships with more diesel powered ships. And a lot of people thought, well, it's just a different diesel, what's the problem? Well, there's a big difference between a 1960s technology diesel engine and a 1990s diesel technology engine. And the complexity of the equipment, the electronics, the control systems was all much more than the organic staff, the existing technicians were trained to manage. And that was readily apparent as soon as we started looking at the configuration of the engines and the maintenance procedures and the list of special equipment that was going to be needed. We're like, wow, our people aren't trained on any of this. So you start to get really smart just reviewing the information that comes out of the maintenance task analysis, and suddenly you're getting to know your physical asset much better. And it's like getting to know someone. It's telling you its story. And it's like, hey, I'm going to need help, and this is how I'm going to need it. And you're like, well, I'm not a certified, I'm not a finance person, or I'm not a lawyer. You need to go hire a lawyer, right? But you've already bought this piece of equipment. It's telling you I need all this work, and you're responsible for making it happen. So you either have to get other resources in place to do it, or you have to invest in your own. So after gathering all that information and analyzing all that information, we are now in a good position to start making some decisions. Now we can make some recommendations at this point about whether we should do the work ourselves. Maybe we should do the work ourselves in a couple of years after we've become more familiar with the equipment and we've given ourselves a chance to get some training, and we've invested over a few years in all the assets we're going to need. Maybe that's the right plan, but we can make those recommendations just off the non-economic analysis. Now what we can do is we can start attaching costs to all of those elements that we discussed: the training, the skill levels, the different numbers of personnel, the resources, right? All of that can have costs associated with it. And what we can do is we can determine, like, hey, we're going to go down to about this point in the engines. We're going to do all the stuff from the cylinder heads up ourselves. But when it comes to like the crankshaft, way down there in the bottom of the engine, the really complex thing, yeah, we're not pulling that out. So what we've done is we've determined equipment hierarchy. Where in the system are we going to draw a line between what we're going to do and what we're going to hire someone else to do? And then what we do is we determine whether we should analyze the costs. If we have alternatives for doing the work, attach all those costs to those things, to all those items, and then we crunch the numbers. And in the end, you're going to have basically an alternatives analysis done, where you could do the work yourself and it's going to cost this much. You could do the work with this resource and it'll cost this much. And you can start comparing those costs. Now, that sounds like it would be enough, and it usually is. But to make a good decision based off of that data, you should do something called a sensitivity analysis. And I prefer a one-way sensitivity analysis just to keep it simple and clean. You find the most unstable variable in all of this. And by the way, it's almost always how long the maintenance task is going to take. Okay, it's almost always the duration of the task. And I say that because the skill levels are fixed. You don't have control over the supply chain costs in many of these situations, and they're limited usually for unique equipment. The cost of oil is the cost of oil, right? Those things you can mess around with. But one of the things you really have control over, but is kind of hard to pin down at first, is how long it's actually going to take to execute the work, and we call that a duration. So the duration of the task, you could feed that into the sensitivity analysis and say, well, if it took us 3 times as long to do this task as we say it should, what's that going to cost us if we had to pay for each of those resources? And that's what we ended up doing in our case study. So we decide on a solution, and then we issue a report, and then we document it. Now, the term L-STAR is not going to make much sense to people outside of the logistics engineering world, but really all it is a repository. It's a database where you document the solution and the decision, and you say, this was the case, this is the decision we made, this is the plan that's put in place, and it's all stored away. So you can reference it later, because this stuff is going to involve some significant amounts of money, as you are getting ready to see. So why look at activity-based perspectives? Well, sustainment is all activity. And with these ships, we had to look at how much we were spending to actually go out and perform the maintenance, because that's what was costing us the unexpected money. We didn't anticipate we were going to spend this much maintaining these vessels. Now we were burdened with the increased costs, a significantly increased cost, way more than we had anticipated when we bought these things. And so we're like, man, we need to kind of get control of these maintenance costs. We're taking money from other assets and other areas of the organization and other programs to fund these repairs, because the operational importance of these assets is superior. We have to have them out there doing their job. So we're going to rob from Peter to pay Paul. And that's not a good solution for long-term sustainment. So we have to get a better handle on these. We have to make better decisions. We have to figure out if we're investing our money in the right place. And so it was really important for us to look at the activities, because those cost way more than just the pump or just the engine cylinder head. And in this case, it was cylinder heads. So we looked at all the depot maintenance for the ship and said, okay, for this engine, this is the one that's really eating our lunch. This equipment's costing us the most money. How do we get control of those costs? And what we found was, after doing the analysis, we identified a potential cost avoidance of $1.6 million just in depot maintenance activities for the main engines on the ships. That's it. If we didn't touch any other equipment, just the main engines, we had a potential cost avoidance of $1.6 million across the fleet. And that was a big chunk of money because $1.6 million is, unplanned expense is not something that any organization is well suited to support. So when you do this, when you take the perspective of activities, what you're doing is you're putting yourself as a manager or an analyst in the position to walk with the maintainer. They're the ones executing the activity. You're putting yourself in a position to experience the supply chain in action. You're putting yourself in a position to understand what the field support entity is going to do. This picture here is my main propulsion division, the guys who had to do the work on these engines. You can count the heads if you'd like. They range from basic laborers all the way to advanced technicians. And there's a lot of money sitting right there in people. And they had zero training on how to support these engines. And they weren't outfitted with the proper equipment or special tools or parts or anything. So we now needed to get them there so they could actually do the work, because what we found was they were significantly cheaper labor than our alternative, which was the original equipment manufacturer. So whatever we could do to use our own people, if it cost less than hiring OEM, we were all in, because we would have some resident knowledge about our equipment. By the way, your assets will thank you because they don't have to wait for other people to show up to fix them. So you can restore your equipment faster. Okay, so let's look at the labor cost comparison. We had three options here. We came up with either we used the Coast Guard's workforce, which is in blue. We could use the orange workforce, which was everyone else, right? Contractors, OEM. And then we could use what was called a blended solution, where we hired one expert technician to come in and use our laborers, which were cheaper labor workforce, right? And kind of strike a healthy balance, because we'd have an expert on site to reduce the risk, an expert on site to guide the procedure, an expert on site to kind of educate our people. And they were getting basically a crash course on how to do this work with this expert on site. It's kind of like hiring an instructor to come in and do the work with your team. And that was indicated in the gray bars here. So for some of these activities, it looks like, it's kind of a wash, but for others, you're like, wow, that's a significant difference in cost. And this all looks nice and everything, but it doesn't really tell the whole story. Each of these activities on the bottom is an individual maintenance activity, and this is them being done once, okay? But you may have to do that turbocharger repair on that exhaust system several times, right? So this is just one instance on one engine of each of these maintenance activities captured. And what we realized was, well, you've got 2 engines on every ship, and we have 11 ships. So if we did all this maintenance one time, and we did it with the right team, we could potentially save $1.6 million across the fleet. Potential, right? So how did we come to a decision? Because that bar chart's nice and all, but it doesn't really jump off the paper and say, ooh, pick me, pick me. So we did a sensitivity analysis. And what we looked at was, hey, what's the one unstable variable? And like I already let the cat out of the bag, that it's task duration. Now, we didn't just assume that. We actually had a whole year's worth of performance data that we could look back and say, hey, how long did it take you guys to do this work on these other pieces of equipment that were just like the ones we just bought? And our maintenance team said, oh, I've got all that data right here. Let me go fish it up. And about a week later, I get a spreadsheet dumped in my lap, and it's got all the maintenance activities and all the labor categories indicated who did what and how long it took them to do the work. And I said, okay, now that you've got that, I want you to go find out how long it should have taken to do the work. And what we found was that it took from a 1.0 is exactly what it's supposed to take you, right? 1.0 is basically the prescribed maintenance duration. And we had a very, very wide range of variance scaling upward, up to 3 times as long to do what was prescribed. So in this case, it'd be like if they said it would take an hour, it was taking the team 3 hours, right? And so that immediately jumped out to us as concerning. So we go back and say, well, maybe this is something that the OEM wouldn't encounter. Maybe this is just an us problem. So we go back to the technicians and we said, why? Why did it take you so much longer to do these work? And they said, well, this engine installed in this ship in this environment with this many hours on it has a lot of complexity in the task that the equipment that's sitting in a lab that's been designed and not in its operational context with no equipment failures and very little hours on it doesn't have. There's other equipment in place because it's in our facility and not in their lab. There is age on the equipment now. There's been temperature fluctuations. So when we go to take the cylinder head bolt off, the head breaks off. That's not in the lab. And so what you realize is like, oh, that operating context, that environmental context around the asset really matters. And it impacts the way you should estimate your labor and your maintenance tasks. And so what we did is we modeled it. We said, okay, well, let's put the costs in for each of these resources. And let's just see what happens if it takes up to 3 times as long to do the work with each of the resources. So 3 hours for our guys, 3 hours for the OEM, and 3 hours longer for the blended team. And really what we found was, boy, if we hire a contractor, this is going to cost us way more than if we do the work ourselves. The contractor is in orange and our team is in blue. But look how close the gray blended team is to our cost of doing it ourselves. And remember all those risk mitigation elements, benefits that we get from having an expert on site? All of a sudden, the blended team seemed like the ideal solution. And we said, why wouldn't we invest a little bit more to buy down all that risk, have an expert on site, but not depend solely on the original equipment manufacturer, and build our proficiency, our competency, and our resources by experiencing the work with our staff, using their expert as a guide. And we said, let's do it. And so we established a contract, and that's what we did. And it was based off of this one sensitivity analysis. This basically helped us make our decision. Okay, so that's the case study. This is me. You can reach me at this email address or at this phone number. And this is what I do for a living. I do this life cycle management stuff, and you can find that stuff at eastpartnership.org. And that is the presentation. So thank you guys so much for paying attention.
Excellent. Thank you so much. Thank you.
Yes,
thank you. Thank you. This is good. I'm just gonna leave your slide up there with the comments and questions, because that works for us. So equally thought-provoking, I would say, Luke. We're gonna head right into the Q&A session, and I really want to thank you guys for keeping to the time. You both came in exactly at the half an hour mark, so that was really, really good. So audience, if you have questions, go ahead and put them in the question box, and that way I will be able to grab them. So I'm going to start with a couple of questions that have come in. So for both Paul and Luke, the results that you presented today were achieved over varying amounts of time. I mean, they just didn't happen all at once, right? So what I'd like to know is what combination of factors led to the organizations deciding to confront the issues that were presented in the case study? And we could start with you, Paul.
I'd say for us, most of the time, it's unhappy operators or maintenance staff. I mean, we see the problems first, and then they end up getting escalated up the chain as need be. You know, we try to solve the problems at our level, and then when we can't, then they go up to engineering and further management, and if they become capital projects or whatever, then that's sort of outside outside of, but I'd say at the end of the day, it's really operators operating the plant. They know what it should do. And when something happens to keep it operating at steady state, they let us know about it. And then we try to get them set back to a good operating state as soon as we can.
Excellent. And Luke?
Yeah, if I'm reading your question properly, our main driver is just operational availability. That piece of equipment influences a greater system, and that system has to be out operating. And if it's not, we have to go get another one. So
Right.
there's like this cascading effect of these critical system failures that we're under a lot of pressure to fix. And it's financially, from a more strategic perspective, there's the pressure of not meeting the mark operationally, but there's also the pressure of increased costs based on trying to correct the measures to get the assets back into service. So we had increasing pressure financially, we have increasing pressure operationally, and all of those things, can cause you to make decisions a certain way. So we, as the engineers and the managers, try to stiff arm the emotions a little bit and say, okay, we have to be logical about this, and we have to be very timely about this. So we have to move out quickly, but we have to make sure we do due diligence. So if we might put some temporary measures in place to restore operational availability while we do some of this long-term analysis.
Excellent. And Paul, you mentioned that many of the BPU results were actually derived through cross-functional input. Case study number 2 in particular was resolved through what I saw was a 4-pronged approach that included a change in the operational strategy to reduce that aqua ammonia from 29% down to 19%. So how did your organization get all the departments such as maintenance and operations and even IT on board with putting together this solution?
Well, regulations drive a little bit of this, and so did HAZOP study and APA Clean Air Act requirements. So that got us really all those groups together at the table to talk about what if scenarios and how to deal with those. So really was a lot of discussions, and if somebody would bring up something somebody else hadn't thought of, then we'd pursue that through Q&A and figure out what a solution was. So just a lot of table talk exercises. They weren't necessarily fun, but they were great at getting at the problems and finding solutions.
Right. And Luke, just so you know, we're still viewing your screen. So if you do put up your baby picture up there, we are gonna see it.
Yeah, I was trying to get the view back up. I can't see any of you, so sorry.
Oh, you can't? Okay.
No,
so,
it's because I went into presentation. I'm sorry. It's okay.
yes.
Oh.
There we go.
There we go. All right. So for this one is for Luke. So supportability analyses have been well established for defense assets. I hear that all the time. What scope do you see for these applications, sustainment analyses such as MT and LoRa for civilian assets, such as those in manufacturing and utilities and so on?
Yeah, I think anyone who does this work in the defense space or in Homeland Security or any complex government body that does supportability analysis, when they work with the civilian counterparts, they're like, oh my gosh, you have no idea what you're missing. Because it's the same problems, right? I mean, it's a different asset, but is it? I mean, it's the same thing. It's just a different function, right? So maybe you don't have weapon systems, okay, but there are plenty of ships out there that aren't military, and those shipping companies aren't doing these things,
Right.
and they actually pay a lot more for maintenance than these government bodies do. So my advice to you is to think about where you could benefit from it strategically. How would it impact your asset management programming if you are experiencing large costs or you're uncomfortable with the risk of not having awareness of life cycle planning for your assets? These are just some of the tools that you could use. There are others. This is not the only way to do business. You can employ some pretty basic but comprehensive investigations and assessments of your own. But do something, because to me it's the lack of planning and effective planning that becomes the problem. It has to be a plan that you're going to do something with. Otherwise, it's just shelfware.
Right.
So the question should be, can I do some work to predict what this is going to cost me? And can I do something about it? And then can I roll out a plan that's actionable? And if you can say yes to all that, it's worth it.
Right. Excellent. I agree wholeheartedly. Back to you, Paul. The role of defect elimination was very clear in your case studies, and that's really to manage risks, minimize losses, and reduce life cycle costs. But some of the costs are not easily unmasked. And I smile as I say that because some of them remain hidden within the business. And one of those was the actual cost of water consumed internally by a water utility. We used to call this, when I was in cement industry, we used to call this cannibalizing your own product. But was the unmasking of the cost of water that the two compressors were using, was that a real learning moment for the organization?
Yeah, I haven't really shared this outside of this presentation internally, except with my director, and that was kind of just telling him some numbers. But this is the sheet I used to make the initial calculations, and I didn't believe it. So I balled it up and threw it away and did it again. I was like, wow, I mean, I can't believe that we all missed that. And so we've kind of talked about some other possibilities now, like when we do a filter wash to restore a filter to another operating cycle. Typically we'll dechlorinate that water and send it on down to the river. Well, we've talked about, let's figure out how much water we use in that process and maybe send it back around the plant now that we've got some sort of tools to think about that. And one great use case, like,
Right.
look at the money we could have saved and the gallons of water that we could have sold had we known this when the plant was designed. Let's take the opportunity now and look at this. Maybe we got some great solutions that nobody's really looked at yet.
Interesting, because I just fresh off of a conversation with one of my clients to make sure that you have an internal electricity rate, even though you are generating power, so that you know what it is that you're consuming within the business. So very, very interesting. Luke, equally,
Yes,
the role of supportability analyses is really to manage risk, minimize losses, and reduce life cycle costs. For LoRa and MTA analyses, tell us, about those hidden costs as well. Within the business, it's hard to find them, but how were you able to unmask some of those hidden costs related to like the mix of maintenance strategy, labor, and parts?
Yeah, so no one had really packaged the cost as an activity and looked at it as like a thing we're going to do. They were very focused on individual costs. They hadn't aggregated them all. So they were like, well, the supply chain implications are over here, but we don't fund that with the same money, so we're just going to not see that. And then the training money, oh, that's funded over here, so we don't really see that. So they didn't really understand what the total cost of an activity was. And there's people making decisions saying, go do this, or don't go do that. And they don't understand what the financial implications are of those decisions until they view them as like, oh, I'm funding an activity and this is how much it costs. So that was one of the things that we gained. The other thing that we gained was when we did the maintenance task analysis, we started asking questions that no one else is asking, like, hey, what are your consumables? Hey, what are these resources that you're just using and getting rid of? And we didn't realize like how much we were spending in disposal or how much waste we had in some of those areas. And then what we found that was really interesting was no one was accounting for hours as costs, because they don't pay in the government for hours of labor. There's no timesheets for active duty members. So they didn't really understand how much time they were spending, how much that labor rate was impacting them until they saw it on paper. They said, oh my gosh, that's crazy. So, sometimes it's just seeing the same information in a different way. And then all of a sudden you understand, like, the things start to click. Paul, I loved your example with the water, because I actually did a capstone on wastewater in a nuclear motor washdown facility one time. And just managing water differently, the wastewater, we saved them like $500,000 a year. And they were floored. And I said, well, if this water was liquid gold, you would have treated it differently, because it would have been spilling all around your feet. And you would have been giving it to the county and paying them to take it. Like, you wouldn't pay anyone to take your gold. They pay you, right? So it was just, to me, it's all about like you gain some perspective that you didn't have before you started.
Right.
And
And I guess I just add on to that, water, we look at rate increases and we have to run those through the state. We can't just increase our rate because, well, we know it's expensive to make water, but when you find places you've been wasting money and missed opportunity and you can correct those, well, maybe that completely eliminates a need to go borrow money because you've stopped the bleeding, so that's
precisely,
That's right.
good stuff.
precisely. Oh, that's excellent. Thank you guys for that. Back to you, Paul. So your organization achieved some phenomenal results by incorporating defect elimination. And I mean, Michelle, if you're out there, I think you're on the webinar. Your ears must be ringing with us saying defect elimination over and over, because we got to talk about that, sister, at some point. But so, by incorporating really what was defect elimination and active risk management for assets. So what tools have you used to support these analyses over the period of the years that you've been doing it?
Control system historian data, that's a phenomenal wealth of information. Our CMMS system for parts and labor and failure modes. And then just some of the predictive tools we have: ultrasound analysis, vibration analysis, soil analysis, infrared, electrical analysis. We've got meters on all sorts of things, and a lot of times that gets really underutilized. So those are really just some of the tools we use a lot of the time.
And you know what? I'll throw that same question to you, Luke.
Can you restate the end of the question? Sorry.
Yeah, so what kind of tools have you used to complete these analyses, like the MTA and the LoRa and so on?
I've used such wild and exotic tools as Excel, feet on ground talking to people, right? So the big thing for us is that there is software out there that can help you with this. I'm obviously being difficult, but there is software that you can purchase if you're going to do like very thorough. You're looking for optimization outputs, like things that it wouldn't make sense. Like you break out your calculator and you go, wait a minute, I shouldn't be doing this. That's when you go buy like software like ASI. They have an Optium solution, which is great. I don't think they have a LoRa modeler right now, but they do have the ability to do a lot of the supportability analysis outside of the LoRa. And to be honest with you, you get so much from them that you may not need to do the rest of it after that. And then there's systems like Opus from Systicon's Opus software, and I think Windchill from PTC is also capable of doing some of the supportability analysis. But yeah, I tend to try and stick to some of the things that we can use a little bit more, maybe things that you already have, right? So we're going to need to access your CMMS. We're going to need to access your ability to manage your finances, so whatever your financial management system is, and then extract data from that, and then move about smartly.
Well done. I think the audience would be quite relieved to hear that there's quite a bit of this that they can do with the tools that they already have in-house.
Yeah, you can do it with just like, you just have to have the ability to build things like think logically through a process, right? So it doesn't hurt to have like a facilitator of someone that does good process facilitation, or maybe someone that specializes in lifecycle management to help you with that, because it really is about like making sure you adhere to the right process as you go through it.
All right. As I have you on the floor, RCM, MTA, and LoRa have one thing in common. They have a high data requirement, data intensive, we call them. So this is a common complaint, actually. What advice would you give to organizations who wish to start using more supportability analyses as a part of their asset risk management programs?
So I would say make sure you stick to the fundamentals, right? Get your maintenance house in order. Make sure that you are able to get some smart people to look at things like, hey, do we have the right stuff? Not just do we have stuff, do we have the right stuff? Do we have good processes in place to do the maintenance? Where are we documenting this stuff? Where are we capturing the data? Is it visible? Is it usable? What's the integrity of the data? Like, regardless of what software solution you have or where you store it or whatever, it's really about the confidence in the data and making sure that the right people are gathering it and the right people are using it, and that you're making educated decisions based off of logical relationships. So you don't make a lot of assumptions, do the hard work to go out there and try and get your finger as close to the real thing as possible. That'd be kind of like my big thing, is just master the fundamentals, make sure you have the right perspective, and that you give people a chance to get the work done properly. Because even though it may feel like, like RCM, for example, if you're looking at RCM for the first time, you might think like, wow, this is a lot of work and I'm not sure if the juice is worth the squeeze.
Right.
But for people that have done RCM, they're like, don't look away. This is great. They understand the value of it because they've been able to improve maintenance programs using that tool. So yeah, that's kind of my advice, is just to make sure you stick to and get the fundamentals down before you move on and try and do something crazy.
Okay, excellent. And Paul, I'm just going to toss that same question at you as well. What kind of advice would you give to persons who want to start collecting more data on their assets and to get that process going so that they can start to look at defect elimination and crunch numbers as you have been doing? What kind of advice would you give to them?
Really consider the sources of information that you already have. If you have a control system, then you already got a historian. If you got a historian, then you've got lots of years of data on all kinds of things. Maybe it's not on a specific piece of equipment. So maybe I wasn't recording air in CFM use by my air compressors, but I should have a meter somewhere that's recording energy off that. I should have another meter somewhere in the plant that's recording water use in the plant. Maybe I can put those together to come up with numbers that weren't specifically recorded from the get-go. So I just say use what you have, and then talk to people. There's when you've got operators and maintainers, you've got all different sorts of time in the job. You've got people that don't necessarily think like you, and they see different problems differently and solutions differently, and those all add value to figuring out, what you can do and what you can't do. And culture is a big one too. What culture prevents or enables a lot of the actions that can be taken to fix things. So you got to consider culture in that calculation somewhere.
Yeah, I love that point, Paul, because I think you have to be intentional, right? You can't just be like wishy-washy, and that's part of the culture. Like, to build an intentional culture,
right?
You absolutely have to do that. And some of that has to do with sponsorship. I know people get a little wonky about sponsorship. But you
need
do.
It.
Yep, you do have to do that.
Absolutely need it. Absolutely, I agree. And this one is for both of you. So what do you see as the next big challenge for your organization? What's that next big asset management mountain that you're trying to climb?
I'll go first on that. For me, since the get-go with asset management, I was introduced to it really here was like an executive sponsor. My director at the time, Kansas Department of Health and Environment, had commissioned EPA Region 7, I think, which was covered by the University of New Mexico Environmental Finance Center, to come up with a way to teach asset management to small and medium-sized water utilities. So they had a program called IAM Can Work, Asset Management Can Work, is KAN for Kansas. And it was like a week or 2-week workshop. I forget how long, it's been too long ago now. It kind of opened my eyes to asset management. And I was like, well, this is really cool stuff. So kind of in all that, I worked to create a sort of an asset management policy for water, and it really didn't go very far. It was adopted sort of as a water division practice, but to make it an asset policy for the entire utility takes upper management board level people. So I worked to sort of educate some of those people that I had contact with, and made some good inroads there. But I think overall for the utility, one of my goals before I retire, or even after I retire and come back maybe as a board member, elected board member, is going to be to get an asset management policy in place for the utility. I mean, if the mission is really to focus on the needs of our customers, to improve the quality of life in our community through safe, sustainable, and reliable utilities, asset management is the enabler that makes all that happen.
Absolutely. I love to hear that. Luke?
Yeah, in my particular case, we're looking at some alternative life cycles, which is kind of politically taboo within large programs because you bought into designing a thing to do a certain thing over a period of time, and we want it to work just like this. These are the design criteria. And then you start building that thing and you realize, wow, that's a pretty restrictive life cycle. Do we have any options? And usually the answer is, I don't know. No one's done the work to see if there's a better way. And so right now what we're doing is we're trying to determine if we have a better life cycle alternative than the one we designed our assets to, assets being the submarines. And if it works out, then we will have a better sustainment and asset management policy in place to actually extract more value from the asset, more operational time, and reduce the burden and cost of maintenance and off time, downtime for the equipment. So we're going to do it's going to take us about another year to really do this the right way, and with enough rigor to go and move mountains, because there's an entire enterprise behind supporting these things. So in order for us to change the way an entire enterprise does business, we kind of have to crunch some numbers and done some, yeah. So that's kind of what we're doing right now. It's just making sure that we have the right life cycle.
Excellent. So you both mentioned at different points in your presentations that this whole thing is a journey. So I'd like to start with you, Paul, and see if you were to start your journey back now, looking back at all the calculations that you're able to run now and everything that you now know, what would you have done differently? What would you have done more of?
Run the other direction. I don't know.
That's my answer.
It's a lot. Really, if I could have started over and done, I really wish I had known about tools like LoRa and PM optimization. Because when I came into this department, I didn't really know any of that. I'd been a maintainer before. I'd spent a couple years in a VOTEC learning how to maintain internal combustion engines, and so I had a natural sort of knack for mechanical things and how they work and how to repair them. But really, those tools like that Lucas talked about would have been fantastic to know about. It would have been those would have been a great start. It really
Great
would have.
place to start. Oh, these kids have it so much better these days. What about you?
I feel the same way Paul does. I wish I knew about this stuff I know now earlier, because I didn't really find this stuff until I had a really strong reason to go look for it. That really strong reason was an admiral telling me, you got to figure out why this happened. And when I went and started digging, and I knew that we should have known this was going to happen, and we should have had a way to figure this out earlier. I just didn't know the answer. And then I find this stuff and I'm like, wait a minute, how come this wasn't done? Look, it's all right here. If we had just done this work, we would have known. And
Right.
so it taught me, I learned the lesson the hard way. I didn't find out about this stuff, then get hurt by it. I got hurt by it. That's how I found out about it. It's like, oh, wait, you guys have cars? I've been walking to work for 20 years. It's like,
But come on.
yeah, starting out as someone executing maintenance, I didn't understand what influenced my work, right? Why am I doing this? Who told me I have to do this? What is the equipment driving this or not? And so learning about RCM and then learning about supportability analysis, I was just like, oh my gosh, now it all makes sense to me. So I wish I'd have known and done earlier.
And it's kind of time, for the young ones to stop getting hurt with these things, and like all this information is out there to start learning, so okay, well, Paul, do you want to share any final thoughts with our audience?
Yeah, I guess it's better to start somewhere. The elephant's awful big, and you can only pick a piece. We'll pick a piece that's easiest and closest to you, to start with. Get some like before and after, information, and then use that to present to somebody. Hey, here's what we did. Go to conferences. I get out of my industry's conferences. I'm obligated to go to a certain amount of them, but I love to get out and go to other conferences like SMRP and International Maintenance Conference and Reliability Conference, and I can see all these other industries have the same problems. They got the same sort of equipment. They make different things with it. They do different things with it. They may not have the advantage of the redundancy that we have in a drinking water treatment plant, because once you start one of these babies up, you really can't shut it down. So it's like you got to keep the bus repaired while it's rolling down the road. Just learn, get to know things, and figure out what you can do to improve your environment.
Excellent. And Luke, can you share any final thoughts with us, as well as, since I'm also a member of East Partnership, let us know how we can learn more about LoRa, RCM, MTA, and the suite of asset management courses that you have at East Partnerships.
That suite of asset management courses is pretty sweet. It's amazing, actually, and I'm kind of jealous every time I see one of the courses. I'm like, man, I'm not that good. I should be that good. Yeah, at East Partnership, we basically try to make as much of this stuff that we specialize in available for other people, so that they have a resource that they can use for training and learning that isn't going to take them away from their work, because we know that, you know, that's a big barrier to education. Like Paul said, we only have so much time to break away from work, and we have to go to conferences, and we need to be part of our community. And so a lot of times we run into the burden of not being able to dive into these resources. And so having the on-demand training opportunities is extremely beneficial to both the managers and the people, because they can work the training around their work schedules. So that's kind of one of our main drivers there at eastpartnership.org. As far as my recommendation about where to go and what to do, besides getting smarter on this stuff and then trying to do something about it, all of this requires change. All of it. Do not fear change. Embrace change. You have no opportunity without change. You have to take advantage of your opportunities to change for the better. Change is not a bad thing. And if you really want to look at the blanket that covers all of us is risk management, right? And when I teach program and project management at the university, I tell everyone, look, get healthy perspectives on risk, because it's unavoidable. And you need to make good decisions based on that stuff. And that means you have to be comfortable with change and challenge. And if you're not being challenged and you're not changing, you're not improving. So my big thing is just embrace the opportunities to change.
And that's excellent, because Luke also hosts Life Cycles Live.
Yes,
and
ma'am.
Next week, we will be talking about change management for asset management. So we hope to see you there. Well, ladies and gentlemen, we have come to the end of our session. On behalf of the Institute of Asset Management Manitoba branch and the Canada chapter, I would like to thank both presenters, Paul Crocker and Dr. Lucas Marino. I can truly say that we have learned a lot from you both today, and I would also like to extend my gratitude to the amazing audience. You have been so attentive, sharing your questions and participating. Thank you so much again, Luke and Paul, if you could remain for a couple of minutes. But thank you so much to everybody. Thank you for your time. We've come to the end of our session. Have an amazing day.
Thank you.
Thank you, guys.